Good morning. What I observe, the gender distribution is almost like my classes, which is a pity because I'm talking about sanity, and in my experience, women are usually much more sane than the nasty boys. So I'm talking about sane and safe C++ class types, and a warning. I have too many slides because I have material around that area for at least a day. And I try to put everything in 45 minutes, and that's not possible, but I try to give you the most important stuff on that way. Who is not a C++ programmer at the moment? Okay, but even you can learn something because I have some wisdom there, some sanity, not from my own making, that you should take away home regardless of what language you're using. So if you look at the dimensions, about 2 years ago I started to work with more closely to work with people who care about safety critical systems, and actually longer ago, but that was when I started seriously looking into what they are trying to achieve, to give guidelines and rules to make code safer. And in C++ we have different areas. We have some areas where you say, okay, it's sane, makes reason, and it's very easy to use, and it stays safe. That's good stuff. That's where you want to be, because then even if you change things, usually nothing bad happens. And then there's a large area that either requires very high discipline, because you might end up in undefined behavior, or might even be a high safety hierarchy, means because it's dangerous and explosive, or even it might go into the insanity of undefined behavior land where anything can happen and you might not even be able to detect it. I've also reviewed code bases where you have, let's say, not too unsafe stuff, but again stuff that's ill-advised, and somehow that's poisonous, actually poisoning all the code base because everybody is doing it, in my opinion, wrongly or badly. And things like, oh, not using cons is in that domain of ill-advised stuff. So I hope it didn't make you too afraid, but I want to cover that area a little bit with some typical C++ types and figure out where they belong, if they are on the high discipline area or even the danger area, or in the easy to use area. And I understand, not always can be in that easy to use area. There might be, because it's C++ and because you want to do something serious stuff, there might be stuff that is in the high discipline area, but please don't go here with your code base. And if you're here, try to get away from that. Scott Myers once wrote, when in doubt, do as the ints do. Integers are great because they can do a lot of things and they just seem to work most of the time. That's why I added to that, but not maybe always. But values are an important thing. Values actually typically end up to be in that easy to use, no need to think about every detail area that you want to be in. And value types, Stepanov, when he created STL, he actually introduced a concept called regular. A regular type or a semi-regular type is something that you can easily use, and if you put it into a container, nothing can go wrong. If you create a vector of int, you have a very hard time to break that vector. So a regular type typically is copyable, it is default constructible, it is equality comparable, that makes it regular, not semi-regular. In Stepanov's sense, regular also means you have the comparison with less than, so you can actually sort things, but not all things need to be sorted, and all kind of things. And sorting will be different in C++20 when we get the spaceship operator, which changes a lot of things or guidelines that you might have already with respect to the comparison stuff. So value types are nice, and the standard library expects them and it works fine with them. How do we get value types? And if I give you a landscape of what kind of types I want to show, we see value types usually are in that area where you have everything is fine, good, great. But there are other kind of class types that we can create. For example, we can create empty types. I will give you a little bit. Empty types usually don't, because they have nothing in there, nothing can go wrong. At least nothing serious can go wrong. We have other things like pointing types, and that's not only pointer. Everything that refers to something else, where lifetime is actually crucial. If you refer to something that's no longer there, you are in deep trouble in C++ if you actually try to use it. And that's where you get easily into undefined behavior land, like a pointer to an object that's already gone. One thing. And using pointing types usually requires to be a highly disciplined programmer to not run into that situation that either they are not initialized properly or they are referring to something that's not there. I introduced a category that's not often actually visible or, let's say, mentally aware about. It's called what I call managing types. Types that control other objects or values. Vector is such a managing type because it controls memory and the elements in the vector. It owns them and it controls the lifetime of them. There are other classes where you might end up writing something called a manager that keeps stuff around. Keeping, let's say, open database connections around, or keeping file handles around that are open because they refer to a socket that you write to or read from. That are typically managing types. A category, what's in a managing type is something that actually stays around longer in your program, and you usually refer to it from down the call chain to get some stuff of it. Some people put managing roles into global objects, which I believe is a big mistake because it's very hard to test to have some global objects around there. So consider stuff that's managing types. And well, you might ask me, why is vector a managing type? Because you can have perceived vector, it's copyable, if you put a vector of int, it's perfectly reasonable to use as a value type. Library experts have the expertise to actually move a managing type to become a value type. But it typically means to jump a lot of hoops, caring about exception safety guarantees and stuff like that. If you write your own vector, even though Bjarne teaches that to you as a first serious class in his books, I believe that's a mistake. You shouldn't write stuff like vector as your first attempt to use C++, because you will get it wrong. Even library writers, even the standard libraries, tends to get stuff wrong. And not by bad intent, it's just very hard to make it right and safe and sane. And a typical implementation that goes along that line is actually on the insanity area to get there. So you more or less have to go down here and then end up here again for your users. And there are other things like plain pointers are just ridiculously dangerous in modern C++, and it should no longer be used. Plain pointers managing memory have no use at all anymore in C++ today. And also I have seen classes with very, let's say, interesting combinations of special member functions. People like, oh, we define a move constructor because we just learned that and forget about move assignment, or don't care about copying, or define a destructor without caring about copying and moving. That's something, there are weird combinations. And you allowed to do that, they will perfectly compile, but they might not be actually very useful for your users. Now, I explained my landscape here, and oh, I forgot about OO polymorphic type. Who is using virtual regularly? Try to get rid of that. It's kind of a drug. It's very rare, especially in let's say, in technical system where you either have an open hierarchy of classes that is extended every other day, the hierarchy itself, and also where you have the runtime variation of behavior. There are a few design patterns like strategy, or composite, where you might end up having things like, okay, I want an OO polymorphic hierarchy, but even those can be changed in C++. Nico Yosutis yesterday showed the trick of using student variant. If the set of classes that are, let's say, form an abstraction or have a common abstraction is closed, you don't extend that. A variant is today a means of implementing that without any needs to go into virtual member functions and polymorphic behavior, and you end up being having value types. There's another approach where you do type erasure to get polymorphic behavior from value types. Sean Parent has a nice talk about that, and I don't have the time to go into details how to do that. But now, where are things like int, double, and bool in that area? I move around and you might shout stop when I reach the area where int is. Nobody's brave enough? Here? Sure? Here? Why?
Well, they are variable types, but you can't guarantee what they represent. So a double 42.7, you don't know what it is.
You don't know what it is. He should give my talk. Now, our primitive language types, sane and safe, let's say they are quite safe to use because they are values, so nothing can go wrong by using them, except we have things like, okay, this is a little piece of code, I have 41, I get modulo 3, and that's not false, so it's true, and then I ask true and I plus 1, so true and 42, and what's the result that comes up here? Yes or no? Any spot the typical mistake? Anybody done that mistake? There are a couple of problems. First, any kind of that's something that is a number can be converted to a Boolean silently without any hassle. And also, Booleans actually promote to integral types, so they are integers, so I can perfectly use a bit and to combine it with an integer. And we have true and 42. Now you have to think about what is a numerical value of true. It's 1. So 1 and 42 bitwise is false. No. So interesting stuff can happen, and it's very hard to spot when reading your code, and this is just a test case to show, okay, write tests. Another thing. I have a vector of doubles using C++17 class template argument deduction and a set of double, and I want to populate the set with all fractions that I can create from the vector elements. So the vector has 4 elements, so there should be maybe 16 candidates to go into the set, and some end up being 1, so the set should have maybe a little bit less. So I said 16 minus 4 because of the ones, plus 1 for the single one that goes in there. And what is the size that we end up really in the end in the set? Very simple, naive code. A few lines of code. Requires a lot of discipline and understanding to see what's happening. Anybody dare to give a guess on the number of elements in the set? Divide by 0. Well, dividing by 0 is well-defined behavior in C++. Yeah. It's double, not integers. What is the size of the set? So I said it's not 16. Maybe it's 13. Is it 13? 12? 10? I know, it's 1. There's exactly one element in the set. Why? That's something everybody that uses, or let's say 99% of the people that use double every day forget about. There's a valid double value called not a number. JavaScript programmers are very familiar with that. Not a number in C++ is defined to be outside of the range of comparable values. So if you compare not a number with any other double number, it's always being false. And if you look at the definition of how a set works and uses stood less, if you compare A less than B and B less than A, and if both return false, A and B are considered equivalent. Now, if you compare 1 with not a number, it's false. If you compare not a number with 1, it's false again, so they are equivalent. And this vector is designed deliberately to start with 0, so the first fraction you create is 0 divided by 0, which results in not a number. So this set actually has one element in there that is not a number. The set gets tainted. No other number can be entered in that set, and it ends up with a size of 1. So much for sanity of built-in types. Anybody knew that? By heart, consciously, every day? Think about not a number. Another thing, a typical loop, people try to prevent that from happening. I just want to print a vector elements backwards. And I know the last index is size minus 1. At least I pretend to know. And y I is greater or equal 0, I output vector y. Is that loop correct? Why?
Size is unsigned.
Yes.
So if you subtract 1, you get a really big number.
If size would be 0, that loop would be really, really big and maybe not terminating. And actually it will never terminate because what is a type that used for I? It's an unsigned. And if I compare an unsigned greater equals 0, what will the compiler create of that? True. It's an endless loop.
The compiler will also tell you that.
It depends. I compiled that code. I might have gotten a warning, but it still runs and just boom. Endless loops are undefined behavior. If you're lucky, the compiler will just remove that loop and do nothing in optimized code. So there are people who try to fix that by making size return an integer. I will show you briefly in a couple of minutes why I believe that's the wrong approach to tackling that problem. So we have integral promotion, we have automatic numeric conversions, and all of these things get in the way, especially the integral promotions. The rule about signed and unsigned and shorts and unsigned longs and doubles, they are really, really hard to know by heart and get right and consciously think about them every day. And then we have these special values for floating point numbers that are often forgotten. Minus infinity plus infinity is okay, but not a number is outside of the realm of comparing. Fortunately, with optional, we now got it right. An empty optional is always less than everything else, but with not a number is not less than minus infinity. So that's the problem there. One thing that we can learn from that is if you ever write a class type that has a single element constructor, always make that explicit. You don't want to have implicit conversions in your type system because that makes a lot of things interesting. It sounds so cool first that your class automatically compares 5 to 5 apples, but you don't want to, let's say, convert the apples back to doubles and then do something interesting with them. Don't. Make that explicit. It should jump into your face if you get things like, oh, size minus 1 sticks around, and if size was 0, it gets a very big number in the unsigned realm. And comparison, if you have comparison, if you put types in a set or any kind of sorted data structure, make sure that's total. the ordering is total, that every element compares well defined with the others in a nice manner. Not a number is not there. So actually you should never create a set of double if you really care about safety, unless you can guarantee you never get not a number, which is a different story. Primitive types have a big problem. Let's say you create a function that takes 3 ints. Very nice, very simple to do. Who has not done that? Okay. Now you call it, and how do you call it correctly? Is it 3 to 1 the right sequence of values, or is it 1 to 3, and which will give you the desired result? It's very hard to know that. Well, today we have CPP reference, so at least for the standard library, it's very quickly to figure out. Sometimes you might even be able to hover in your IDE and it will tell you something about at least the parameter names. There are people who want to get there where you want to have named parameters, so you can actually have default values for some parameter in the middle. But I believe that's curing a symptom and not solving the real problem. In C++, we can actually wrap the primitive types to have a real meaning and have the type system and the compiler tell us if we do something wrong. If we wrap things like that, especially if we wrap a single value in a class type, we have to be aware of something. That's something where the standard library is unaware of, and that's giving us the problem of that size -1 problem. We have things that count stuff like size t or size type in the containers. You cannot have negative values. It's 0, nothing, 1, 2, 3, or more. And that's where the natural numbers, including 0, actually have a nice property. But those values are absolute. You might add, let's say, 5 apples and 10 apples and get 15 apples, so you have a count that increases. But if you subtract 5 from 15 or 15 from 5, how many apples do you have if you subtract 15 apples from 5 apples? -10? Can you represent -10 apples? Maybe on a bank account, having a future of apples. There's a different type in the standard library, putative t or difference type, that's the distance between 2 counts or between 2 pointers, which more or less count bytes in your memory. And that distance can actually go backwards. So today this is a signed integer type. The problem is if you subtract 15 apples from 5 apples, you should get a distance. Oh, there are 10 less, which is a distance, and not an absolute number anymore. So I'm talking about absolute values and relative values. And just an example from the standard library. This is GCC library code from one of the, I believe it's vector inside, some vector or some algorithm inside. Distance actually computes the distance in return type, difference type, or putative t between 2 iterators. It's immediately transformed silently, implicitly with the assignment operator initialization to an unsigned size type. You wonder, why is that? I actually cheat the type system. I change the type while initialization that. And this might actually be negative. Maybe first and last are ordered in a way that in practice it will never be negative, but you never know. You could have 0 and -1 and then end up in a very big number. And the reason is the compiler will actually barf at you if you compare an unsigned value, which is capacity minus size, with a signed value. And that's why they made size type n a size type. But later on, it's used as a difference type again, so it's casted down here. When I've seen that code, I said, WTF. Okay, more on that later. So, my perception of ints, doubles, and unsigned, and ints even are worse because ints have undefined behavior and overflow. We don't have access to the carry bit. We just get whatever we get. Unicorns, rainbows, pink elephants. Doubles has that not nice, not a number thing. And unsigned are almost safe to use, but very hard to get right because of here. Very often they represent absolute values, and subtracting one absolute value from the other should give you a relative value, which is assigned integer type. So actually, unsigned subtraction should result in an integer type, which we don't have in the language, and we can't change that in the language because of C. C got it wrong already, but C didn't have really a type system. It stemmed from B, which didn't have a type system at all. Everything was a word. And even string is in that area where it might actually go here in the high discipline area, because sometimes strings, how do you call correctly instead of our nice function with 3 ints? What is if you have a function taking 3 string parameters? Which sequence are the arguments given? And I want to show you something that's called the whole value pattern, and I need to speed up to give you something about that. And the whole value pattern is more than 20 years old. It was, okay, I don't go into that detail, just show you the whole value pattern. Ward Cunningham, the inventor of the web, and many other things that you might take for granted now, and nobody knows that he invented that, wrote the checks pattern language around 1996 or 5 or 7 something. I didn't check the date exactly, and that is text taken from there. And he's talking in the more or less in the Smalltalk realm, but it's more or less timeless, without bound to a specific language, maybe only the wording there. If you have some quantities in a model, and very often you just want to use int or double or even string for that are the fundamental things in your language or library that you can use. And he says, this is no longer necessary. It was standard in languages with weak or no abstraction, like C, that's my addition. It actually interferes with smooth and proper communication between parts of your program and with its users. Because bits, strings, and numbers can be used to represent almost anything. Any one in isolation means almost nothing. So if you have a parameter with an int or an unsigned or whatever primitive type, think twice, what does it represent? And Ward's recommendation is construct special values, so special types for your domain model or for any kind of model in your system, and use these values as the arguments of the messages, translated to C++ as the parameter types of the functions, and the units of input and output for your system. Make sure these objects capture the whole quantity with all its implications beyond Beerly magnitude. That means you should provide the corresponding required functions and operators, returning the corresponding result types that actually fit. Like if you have a type representing an absolute integral value, if you subtract these, return a relative integral value, so a signed integer, for example, or a wrapped signed integer. Include format converters in your user interface that can correctly and reliably construct these objects, constructors, and I/O, but do not expect your domain model to handle string or numeric representation of the same information. So once you're committed to that abstraction, use it throughout your system. Don't make it automatically convert to int and back. No implicit conversions. Take that home. If you take one thing home today, take that home. That's an old stuff, almost always forgotten because we're too lazy. And in C++, actually, doing that just requires this. That's a minimal amount of things that you can do. My example had counters that were unsigned. And if you make your counter wrap it in a struct, it's a different type. It's the same size as size t, but it's a different type, so you can distinguish different counters. Counters for weight and counters for notifiers, even though they are completely the same. You might end up overloading operators. This is not the recommended way to do that, but in C++ you can even make it work in a way that you want to do it, but you can guarantee if you subtract 2 weight counters, you don't get a weight counter. You get the difference between weight counters, which is a different type. Now in C++ 17 on, using these kinds of aggregate types with a single element actually makes them more, you can extend them now by inheriting. So you can actually add operators like that by inheriting and using the curiously recurring template parameter pattern to get there. And I might not have the time to show you that, but I might try. Another thing, if I do these value types and these wrappers, should I make a value type default constructible? Should I have a default constructor either by declaring it or by implicitly getting it? And there is actually one yes, and most of them are no's. Whenever there's a natural default value or a neutral value in the major domain operation, then you can default construct it and provide a default constructor, at best by, if you have to declare it because you have other constructors, equal default. Very often you need to guarantee, or sometimes you need to guarantee a class invariant. So you have input parameters that actually define the initial state, and these must follow some given rules. That often means you don't have a default constructor, and that might end up, it's okay to be okay if you don't have really a default value in your domain. Sometimes people want to have a default constructor because they have to piecemeal construct the value. Like, oh, I want to initialize it, but I don't know if it's A or B because I have another condition I have to rely on to actually initialize that value. I believe that maybe should be actually no, because today we have either the conditional operator to give the corresponding result, or an in-place called lambda if the initialization is complex, and we don't want and we want to have that piecemeal somehow. And again, we have seen that already in some other areas. If there's no natural default value in your domain abstraction, like, oh, we have playing cards, we have in poker, we have all kind of things of some kind of colors, and there is no what is a default card? Is this ace of spades or ace of hearts or a two of whatever? There shouldn't be a default constructor. And also when the type invariant requires a reasonable initialization, and there are some things where you don't want to have a default constructed thing, like a cryptographic key without a decent seed is very, very bad. So you don't want to have a cryptographic key class, even if it's just a big numerical value, to be default constructible, because your users might use it wrongly or not safely. And you get all kind of bad things in your libraries that care about cryptography. Now back to our example from before with our size, time, and capacity. I want to repeat that because I tried to explain it, but this slide has been explained. So distance is actually a relative type, and subtracting capacity from size from capacity in a vector also means it's a relative. It's how much space is left. It's always positive if you do the subtraction here, but again, you might flip it around, and if one might be bigger, or if your vector is implemented wrongly, it might actually be -1 because you exceeded the size. The size exceeds the capacity because you did something wrong. Things like that might happen. So actually, this is a relative. You subtract 15 apples from 5 apples, so you get the difference in apples. So this is actually relative size, but the result type, because both are unsigned, and subtraction of unsigned doesn't give us a signed value, but an unsigned value, that is the problem here. So to be honest, n should have been difference type, so auto here, and here we should have actually cast this part to the difference type instead of recasting n to difference type in these areas. The best example to understand that relative versus absolute is std chrono that we have in the C++ library since 2011, where we have time points and duration. Time point is the absolute thing and duration is the relative thing. While you can subtract 2 time points, you always end up getting a duration and not getting a new time point. You can add a duration to a time point and get a new time point. Adding 2 time points is nonsense. In contrast, adding 2, let's say, counts is reasonable because they are always 0-based, but a time point has an arbitrary starting time. We don't represent time points from the beginning because we don't know when the beginning was. It's arbitrary, so adding time points is nonsense. Adding duration gives a longer duration, which is sane and reasonable. And this differentiation is very often forgotten when you model units. For example, anybody using something called vec3 or vec3d or vec2 or 2D points? That is a type that represents maybe 3 integers or 3 double values, and it can have 2 roles. One is the absolute role in a coordinate system, a given position, and the other role is the displacement, the actual vector pointing somewhere, and that's the relative. So actually, these types should have 2 different incarnations, one for the absolute values and one for the relative values, actually distinguish them and have arithmetic around that. I haven't yet seen a system where that is made that way, that distinction is made. And that's where all kind of bugs come from, like this ugly stuff here. And especially if you write a generic unit library, which I tried and failed so far to get there, you must make the distinction, absolute and relative values. Now, there are people working on strong types. I myself tried that again, especially aggregates that inherit. That's something what I am trying to make up. Like, okay, weightcounter is a strong unsigned, taking weightcounter as a CRTP argument. So that's actually a type encapsulating an unsigned. So weightcounter consists of a single unsigned and provides operations for equality comparison, increment, and output. And there's a static assert that is not bigger than an unsigned. So there's no overhead having these kind of features, but I have a limitation in the number of operations that I'm allowed to do. I only can increment it, it's a counter, and nothing else, and I can compare it to have assert equal. And I also have something that I'm not sure if I should call it that way, but get actually breaks the encapsulation to get out the underlying value, which is kind of unconsciously standardized by the standard library, all kinds of wrappers that provide access to the underlying wrap thing like unique pointer now implement get to allow to access that. So grab get in your code and you see where the encapsulation is broken up. Empty classes, something for nothing. In C++, you get something for nothing, and empty classes typically can be used with emptybase class optimization and CRTP mixins to stay here in that realm by making better, nicer value types. Sometimes they are used as tags and traits with managing types or polymorphic types, and that's where empty types can actually be useful. Who has written an empty class type with no data members? Who has used an empty class type with no data members? Traits. So there are different things. One thing is iterator tags. Yeah, all have used that without knowing when you call the standard library function, because tag dispatch is used there to get the best optimized version of an algorithm, and that's the mechanics how it's going on. I don't want to go into details. There's also traits, which are empty types that just have mechanics for getting at compile time interesting values from other things like with template specialization, figuring out what stuff is going on. And we have the emptybase class optimization. There are some tricky things to get it really work. For example, if you have an empty type, it's not actually empty, because every type has to have some location, and you only get a location when there is a byte hanging around somewhere that you can point to. If you combine empty types with something that has something in it, then the combined type is actually, the empty type is not adding place to that plain type, because there is nothing to access there, but there is already a space for the plain type. That's where the emptybase class optimization actually works. And you need to come to my lecture to learn more about that. And we might actually get that for empty members as well in C++20 with an attribute called noUniqueAddress, but I'm not sure we don't have that yet. So where it's not working, that's a glimpse of what I'm trying to achieve with my strong typing thing. That's the version without the get to fit on the slide. So for example, the equality class type is actually a mix in, it doesn't have any real members, and it's mixing in the equality comparison operator to the U type to be able to compare that, and it's using, how do you call that? Blackout. It's using a C++ 17 mechanism where you say, okay, I access the members of a structure tuple, and just take the const reference to the members, and because there's only a single member, that list consists of a single element, and I know it's always a single member, so this equality thing not only works for types that use that strong, but also for your types that just wrap a single value, and you can use that as a mix-in base class for your type. And adapters is something else that's empty, but they require a lot of discipline, where you can, with inheriting constructors that we get from C++ 17, this is a set that actually provides index access to the set elements, so you can write your strange loops with that. And that's an empty adapter, not adding members to the set, but inheriting from the set. Using these adapters typically requires that you exclusively use the adapter and not the base class, and never actually upcast to the base class, which requires discipline to make it right. And I'm sure I lost you, but we're running out of time. Pointing types require high discipline, and that's pointers, reference, and all kind of smart things. Smart pointers might go into the managing area, so a unique pointer is actually a managing type that is a pointing type. So a lot of managing types, if you have a manager that you have to pass down the call chain to actually have global, let's say semi-global state, you might need a pointing type like a reference. Or polymorphic type, to actually have that dynamic polymorphism, you need a pointing type, a reference, or a pointer to actually make use of virtual. If you only pass pointing types down the call chain, then lifetime management is easy. And that makes it safe and sane. Whenever you keep something hanging around that you pass sideways or up the call chain, make sure you have lifetime extension, either by having a managing type or some other means that is not going away. Very bad things happen if the pointing types is nullable, so it might point to nothing. That's a danger. And the biggest danger is dangling pointing types. Something dangles. If it points to something that's no longer there, and that's the biggest danger. That's where the high discipline actually kicks in, where you have to make sure it's not dangling. And there are things that are pointing types that are not pointers, like iterators. Who has ever made a bug because an iterator was invalidated? Yeah. So, dangling. Smart pointers, reference wrappers, which is underappreciated, and I'm not sure if my ideas of using it more is actually a good idea, but maybe. And now we get views like string view and spans. So it's not only pointer, a string view or a span that we might get in 20 is really a referencing, a pointing type, where you have the danger of it being dangling. And there are some pointing types that have interesting behavior, like const reference, that do lifetime extension, but only. And that but only is almost as intricate as the rules for some integral promotion. You never know if you're doing it right. You make a tiny change and you break it because it becomes dangling. Iterators, yes. Pointers, no pointers. My guideline today is no plain pointers, not even for a single element thing like the core guidelines say. Because when you see a pointer, you know, okay, this is a place where I have to refactor. And tell the user what the pointer actually means, if it's really a pointer. And very often the pointers are used without any need. And no C-style arrays, they are not fitting well into the C++ type system because they decay to pointers as well, and not even pointer arithmetic. Who has seen code like that? One of PI. Don't. That's something inherited from B and C. Don't. It's very confusing for those who have not used that language, and it's something you wouldn't want to do. And its pointer arithmetic is bad. Very, very bad. Managers. It's a term that Richard Corden invented. He told me, oh, I have these object types that don't inherit, but they are still encapsulating interesting stuff and have state that changes and that's relevant. And he coined the term monomorphic object types sitting next to me. And I'm not sure if that's a good idea, but it's not polymorphic. So no inheritance, just encapsulation. And that's important to do that. And sometimes you have that kind of state, at least as long as you're not thinking in values exclusively. Any Haskell programmers here? These managing things are kind of, okay, we have state that might change. It goes into the direction of monads. Not exactly a monad, but something. So if we have these managing types, we can actually make them more sane and safe by making them move only. So we actually are not copying some resources around, or we can have RAII, or we can actually have the magic of vector where we make it a value type with a lot of effort to make it right. And another effort on the template arguments. And pointing types are also safe and sane, as I said, if we only use them down the call chain. And I don't want to go into details because we're running out of time. Don't write your own generic RAII wrapper. A non-generic one is okay-ish, but wait for C++20's unique resource. I hope we will get that. Dynamic polymorphism, Sean Parent says, inheritance is a base class of all evil. And it's much overused. We were trained, at least of my age, in object orientation, but we forgot very often about the biggest advantage is encapsulation first. All that inheritance stuff is tricky and hard to get right and usually used much too often. Abstractions, but many abstractions don't share that much of commonality. Who knows that table by Howard Hinand? When you write some constructor or special member function, what do you actually get? If you don't know the table, go to Howard Hinand's talk in ACCU 2013 and let it explain to you. And there are some bugs in the standard that we can get rid of, like, oh, I define a destructor, but still my class stays copyable. And that's one of the curses of dynamic polymorphic type. We have that user declared destructor, virtual, defaulted even, but still your class is copyable, and it shouldn't be. Because copying in an inheritance hierarchy very often leads to slicing and getting bad stuff happening. And also what's interesting, if you define a move assignment operator, you still get a default constructor, a default destructor, no copying and no move operation. And if you declare that deleted, you never will be able to move it. And that's a good thing. Some types, especially the managed types, should not be moved around. They just should stick there. And that's my recommendation. If you write OO polymorphic base classes, declare a destructor and declare a deleted move assignment operator, and you get no copying and no moving, which is a good thing for polymorphic types. And I will put my slides up online on my private wiki. And almost all hierarchies are wrong, and that are the same combinations of classes, and the constructors are different. So aggregates don't have a constructor. All fields are public, or all members are public. So you get all defaulted operations, they just work. Unless you have a member that's non-copyable, then you get a move only or non-movable. But again, things usually just work. Simple value classes might have a constructor. So you might either resurrect the default constructor if there's a reasonable default value, Or you might not have a default constructor because your class guarantees an invariant. Like, oh, an integer that's never 0 because you want to divide by it. That could be an interesting value type that you might use in your domain. We have manager types that very often have a constructor, maybe have a default constructor, but usually not, where destructor and any kind of moving around is expert level coding. RAI have some constructor, no default constructor, usually at least. Have a user declared destructor, which can also be very expert level to get it right, and are usually not copyable and might be movable or not. Because today we can actually have local variables of RAI type and they don't have to move around or copy around. And even you can return them from a factory in C++17 without being movable, and it's safe and sane. OO, danger, lurking, maybe constructor, no copy, no movement. That is my recommendation. Don't copy or move polymorphic types. At least not with the standard mechanism. There are people trying to get deep cloning smart pointer in the standard library. I thought it was a good idea. Today I think it's not a good idea. If you have OO polymorphism, virtual member functions don't copy. Manager classes, okay, they are good, but if you want to have value properties, copying and moving are expert level implementation and very easy to get wrong. Like forgetting to move the base class and stuff like that, it's very easy to get wrong and sometimes very hard to test, especially if the manager class is a kind of a generic class. You might actually write interesting template argument types for your test cases, like, okay, a type that's non-copyable, non-movable, or throws on every second attempt to copy and make sure that your class actually doesn't barf at you or is broken from that. And there are other means. Look at Sean Parent's talk. So if you look at our landscape, don't go here, stay here, make your classes whole value patterns. That's my message today. And takeaways. Appreciate the C++ type system. Whenever you write a cast, it's a time to stop and think and refactor. Consider each cast that you write an indication of a problem in your modeling of the system. Try to model with value types first. Be aware of relative versus absolute dimensions if you have kind of units in your system. Wrap all kind of primitives using whole value. I consider using int a bug, a design bug. Be aware of the required expert, especially in a safety critical system, because an int can represent everything. It doesn't mean, it means nothing. And you want the meaning in your code to be maintainable and understandable, and have the compiler actually check that you misused it. Be aware of the required expertise, and it's not only Scott Myers alone that you need to learn by heart to make the managers and OO hierarchies correct. Be very disciplined about using pointing types. We cannot get rid of them completely, but be careful and understand the implications of the potential dangling and the and run away from types that have weird special member function combinations, which might even be legacy types that define copies without caring about moves and stuff like that, or define destructors without caring about copy and moves. Very bad things. And that's it. Here's a question. I have 2 hats to give away, and we're running out of time. Question. There was one there, and you both get a hat. So you first.
You mentioned the spaceship operator in C++20.
Yeah.
Does that affect how you would recommend writing comparison operators, say, in C++11 today?
Well, in C++11 you don't have spaceship, but let's say you only have to write the spaceship operator, and then you get all the other comparisons for free automatically by the compiler.
Yeah, but today in 11 you wouldn't change anything if you
Today you wouldn't change anything. What you might do is use that empty base class optimization trick to actually mix in the comparison operators for your type, but not anything today. There's nothing you can do today because the compilers don't give you a spaceship. Another question?
I would like your view on your example with playing cards where you have no default value. In practice, people tend to just pick one if there's no default constructor.
Don't.
Represent unknown.
Today, let's say you can use vector with types that are not default constructible. It requires a lot of, let's say, implementation effort on the side of vector, but you can do that. So there's no need for having everything.
I'm talking about STL, but if you use your playing card in a structure and someone further down the line would like to use this structure but doesn't know that playing card, he or she will pick your clubs.
Well, even if it's not default constructible, you can actually, if you use it and know, okay, for me it's always the ace of hearts that's the default value, then you can provide that default value in the member definition as a member initializer. And then it's in that usage domain, that's the default value, but not for a playing card. What is a default playing card? There is no reasonable default, maybe except for Joker. So the usage can provide a default value, but that's deliberate there, not an implicit default value. There's no reasonable implicit default value. There was another question, or someone ran out? I think we need to stop now because we want to change rooms and maybe have a break. Thank you a lot.